So good afternoon, students. You should have received your midterms results. So hopefully you click on the question parts and then you can see the score and then you can also see the comments given. Okay, so some of the students in the morning class have bargained for some marks already. You can also do the same, right? But if you want to bargain for marks, no problem, but you must have a good reason. So dependent on the comments given, you look at your solution. Then did you address what is given in the comments or not? Meaning to say, if I say that you never do this thing, right, then I minus 2 marks. But actually you did this thing, just that maybe I didn't see. Then you can come and tell me, okay, actually you did this part here, right? So then I'll give you the extra 2 marks back. Okay, so please review through the question parts and see if you agree with the comments that are given. You don't agree, right? You can always email or come and see me to get back your extra marks. So that'll be for the midterms. And then today we are going to continue with topic 6. So looking at the response of the morning class, the second part of topic 6 is kind of difficult. Okay, so I'm going to go through a little bit more slowly for your class here. So then let's recap, and that is on the partial differentiation or partial derivatives. So partial derivatives in a nutshell is really just differentiating with respect to a single variable while keeping the others as constant. Okay? So because that's how it is being defined, right? That means you can see that the limit operation is taken on, for example, in the x direction. So x plus h minus x. Right? So f of x plus h minus f of x. So this is implying that you are moving in the x direction by a step size of h. Okay, then you're looking at what are the changes. What is the change in the function f divided by the change in the x direction. Okay, meaning to say the step size in the x direction. So therefore this is the derivative with respect to x. Okay, and you can see that the y is being held constant. So correspondingly, if you are performing or evaluating the partial derivative with respect to y, then you hold the x as constant, okay, because you are taking the step in the y direction. So therefore, actually partial derivatives, after you practice a few rounds, you will find that they are very easy, okay, because you just really hold the rest of the things as constants. So then we also gone through what is the graphical meaning, right? The graphical meaning is actually very important because if you truly want to understand partial derivatives, you have to look at the graph. You have to understand it from the graph. So therefore, you can see that, like say for example, for this expression, x squared plus x squared plus xy plus y squared, then if you take the partial derivative with respect to x, del f del x, then you can realize that the function is just 2x plus y. Okay, so 2x plus y means that this expression says that the partial derivative with respect to x is dependent on x and y. Okay, so at any x, any y, a coordinate is going to give you a different partial derivative value. Okay, so therefore, when y equals to 1, what does that mean? So when y equals to 1, that means you're actually looking at the intersection curve, the red curve, between the plane at y equals to 1, a vertical plane, and the surface of the function. Then at x equals to 1, for example, means you have locked the plane at 1. Now you look at the intersection curve in red. Then you are evaluating what is the slope of the tangent at x equals to 1. So that's the meaning. That's the meaning of f sub x at some x equals to 1 and some y equals to 1. Okay, and of course the graph must agree with the value that you have calculated. Okay, that means the slope of the tangent line, if you estimate from the graph, right, must be in agreement with that calculated from the partial derivative, because that's exactly what it means, slope of the tangent. So then we also looked at f sub y. Okay, so f sub y is really just similar to f sub x, but in this case, because you are doing f sub y, right? So it means to say that you have to lock a plane that is at a position x. So for example, at x equals to 0 is this plane, this orange color plane. Okay, but it can well be other values of x, because dependent on what is the partial derivative you want to find at the x value for. Okay, so I can also say that, oh, this one can be at x equals to minus 1. Can also be at x equals to minus 2. So you can see, I can change the plane location. So I've demonstrated for x equals to 0. So at x equals to 0, you have a plane, and then it is going to intersect with the function curve, or sorry, function surface, and you're going to get this blue curve here. Okay, so if you view the blue curve here squarely, you're going to see this lah, right? And then you can imagine that actually this is just a function of y. Why is that so? Because this is at x equals to 0, what? So you sub x equals to 0 into the function f, this function f. So your x equals to 0, you're going to get 0 plus y square, ma. There, it's exactly this, 0 plus y square. And therefore, you're just getting a function of y, what? So a function of y equals to y square is just this curve, oh? That's the meaning of the curve. That's the meaning of the intersection curve. Okay, after you sub in whatever x value into the f of xy. Okay, then after that, if you sub in also the y value, for example, at y equals to minus 1, you can see from here, y equals to minus 1, project across. Then that means you are looking for the partial derivative at 0, minus 1. X equals to 0, y equals to minus 1. Okay, so which means that you can draw a tangent line. For example, a tangent line here, right? Then you can calculate the value from the partial derivative. Okay, because this one, the value is x plus 2y, ma. So x is 0, but y is minus 1, so you get minus 2. Oh. Okay, just using the function x plus 2y to calculate. So from here, you can get, oh, okay, it's actually calculated the other side. You see, right here. Okay, x plus 2y. Can okay? So that also implies that if you want to know what is a g prime y, it's going to be minus 2. Oh. Let's say, for example, you look at this expression. So that means, let's say, for example, let's say this is x equals, this is y equals to 0. Okay, because it's y square, ma, so I just make this as y equals to 0 at the minimum. Then you have x equals to minus 1, y equals to minus 1, which is here, for example. So this is minus 1. Minus 1 in y lah. Then you draw the tangent, which is this thing. Okay, you draw the tangent. So then maybe you might be interested, oh, what is the slope of the tangent? So the slope of the tangent is g prime y. So g prime y at y equals to minus 1. G prime at minus 1 must be minus 2. Must be minus 2. Okay, because this is exactly f sub y at 0 minus 1. It's the same thing. Isn't this the same thing? G prime y is the slope of this line. F sub y at 0 minus 1 is also the slope of this line. So they must be the same, what? Is that alright? Okay? So hopefully you can see the comparison here. What is the meaning of your f sub y? Okay? Yeah, so then this is where we left off yesterday. So actually this one, just using your partial differentiation in the functions given. Okay, so we're going to go through slowly. So you see, this is my function f of xy. So now I want to evaluate the partial derivatives. That means I got to write down what is f sub x and f sub y, right? Because I have two independent variables. So therefore, f can change with respect to x and f can change with respect to y. So therefore, I need to write down the two partial derivatives. Okay, so let's take a look at how you differentiate. So differentiating with respect to x. So hence, you just hold the y as a constant. And because you have x times e to the xy, right? So therefore, this is function of x times function of x. So therefore, you got to use product rule. Is it product rule? Then you differentiate x first, whole e to the xy. There, e to the xy. Plus, whole x, differentiate e to the xy. So when you're differentiating e to the xy, you have to apply the chain rule. Okay, so you get e to the xy. Next, you have to multiply by differentiation of the exponent, xy. But y is a constant, so it's like differentiating kx. So therefore, you get k, right? It's just that the k is y here. So therefore the constant is y, so therefore you chain rule down the constant y. So this is the product rule when you differentiate the first term. Then next is the second term. Second term is just a function of x, so no need product rule. Because y is a constant ma. So differentiate ln xy, you get 1 over xy. Then your chain rule, once again differentiating xy will give you y. So that is the complete derivative expression for f sub x. Any questions on this solution, this answer? Okay, so if you understand this, then you must be able to do f sub y also. Because f sub y is the same thing, right? It's just that you are differentiating with respect to y. Okay, then take note that when you're differentiating this xe, xy with respect to y, right? Actually, there is no two functions multiplied together because x is now the constant. So if x is a constant, just keep the x. Then after that, differentiate e to the xy with respect to y. So now you can see that the chain rule must give you x because you're now differentiating with respect to y. Right? So x is the constant. Okay, so that's the first term. Then the second term, same thing. 1 over xy. But now you have to differentiate xy with respect to y. So then the chain rule is going to give you x. Because you are differentiating xy with respect to y. So x is the constant. Is that right? So therefore you get this second expression for f sub y. So next, for part B. So for part B, right, you have sine x over 1 plus xy. So differentiating with respect to x to get your g sub x, you must differentiate sine first. So you get cosine. Then you put back the angle. Okay, the argument no change. But you need to use chain rule, right? So when you're differentiating this fraction with respect to x, that means the constant is 1 over 1 plus 2y. Because it's just 1 over 1 plus 2y times x ma. So therefore the chain rule is going to give you 1 over 1 plus 2y. Because you differentiated away the x already. Can So that's the answer. Then for g sub y, the approach is similar. Differentiate sine, get cosine. Okay, now when you're differentiating this with respect to y, you can see that the y term is at the denominator. X is a constant. So I just factorize out the x first. Okay, since it's a constant. Then I just differentiate 1 plus 2y to the power of minus 1. So I just bring down minus 1. There, minus 1. Can Then the power become minus 2. So therefore it is at the denominator. Then I need to use chain rule. Because I need to differentiate 1 plus 2y with respect to y. So I get 2. You see? So you apply the chain rule twice. So therefore, consolidating the terms, you have this as the solution. Any questions with g sub x and g sub y? Good. So part C. Okay, part C, z to the power xy. So because you have x, y, z as your independent variables, so therefore you can do 3 partial derivatives. Respect to x, respect to y, respect to z. Then, how to differentiate this respect to x? That means z and y are constants. So when you differentiate, this is like a to the power of kx. So you can see differentiating a to the power of x is a to the power of x ln a. This one comes from your topic 2 or topic 3 for single variable functions. The same thing. So you just put back z to the power of xy. Now what's the base? The base is z ma. So you have to ln z. Okay? Then you not to forget, because your exponent is xy, so you got to use the chain rule. Differentiate xy with respect to x. So therefore you are left with y. Then h sub y, same thing. Okay, it's just that z is still a constant. Now x becomes the constant. So therefore you can see the chain rule is going to give you x at the last term. Differentiate h with respect to z. Now z is the variable. Then the power xy is a constant. So therefore this is just like differentiating using the power rule. Differentiate x to the power of k, you just bring down the k, then after the power minus 1. Exactly what I have written here. Bring down the power xy, then the power xy just minus 1. Is that okay? Any questions? Good. Okay, so I don't think any more students will be coming. So we want to, I'm not sure if, who are the Muslim students here? One? No one else? So what I want to propose is that we start the lesson at 1 p.m. so that we don't need to wait like, for you guys like 2.5 hours. I have to wait 2 hours. So if we start at 1 p.m., we will end at 3 p.m. Okay, because in any case, the room is also not occupied from 12 onwards. Because 12 to 2, why is it that they put the tutorial at 2, right? This tutorial at 2 is because 12 to 2 by right is catered to Muslim prayers. Yeah, but then if the Muslims in the class are okay to start at 1, then we can start at 1. Any objections or not? No objections? The Muslim in the class, you okay or not? Are you okay to start at 1? Or you prefer to start at 2? You start at 1, You sure you're okay or not? Because I have to make sure you're okay with it. So you went for your prayers at 12, is it? Earlier? Huh? You don't go prayers. So that's totally fine. Okay, so maybe in that case, right, then we'll start at 1 from next week onwards. Okay, So this one is, I don't make the announcement because this is a bit illegal. Okay? So I tell you, you know right? So from next week onwards, right, we'll start at 1. Can Okay, that's good. So we can all go back together. I mean, all go back earlier. Okay, so this one, implicit, right? Implicit. Okay, I think I want to, okay, this one when you see this thing, right, it's a bit messy. So I better rewrite the whole thing again with you. Okay, so now, it is told that, right, that you have an implicit function of the implicit function z as a function of xy. Okay? So that means this z is a function of the other two variables x and y. Okay? But they give you an equation, right? So it's similar to the implicit differentiation for single variable functions. Okay? But it's just that now, right, you have z as a function of xy. So therefore, you want to evaluate the partial derivatives, which will be what? Which will be z sub x and z sub y. So it's del f del z and del f del y. Okay? So now, you are going to differentiate this equation implicitly. So first of all, del x, because you want z sub x. So differentiate the whole equation using the implicit differentiation, and you are going to get the first term, 3x squared. This one easy peasy, right? Because differentiate x cubed with respect to x, so therefore just get 3x squared. Then differentiate y cubed with respect to x. So y is treated as the constant, so 0. Okay, then this part, right, z cubed. Now when you differentiate z cubed with respect to x, you have to understand that z is a function of x. So this guy, z as a function of x. Okay, z is actually a function of x and y, but z is a function of x. Okay, and you are having a cube. So what is this? This is like a composite function, because z cube is like a function. So therefore, this is what? This is like g as a function of z is equal to z cubed. Okay? So therefore, when you differentiate this z cube, right, you must use chain rule. So del x, this del x, when you apply on z cube, which is a function of xy, is like del x g, apply on g of z of xy, which means that you got to differentiate g with respect to z first. Del g del x, del g del z times del z del x. Is that right? So this is your chain rule, right? Because this is a composite function. Okay? So therefore you have to use the chain rule. That's what implicit differentiation is, It's just using chain rule. So what is this? Z cubed. When you differentiate with respect to x. So dg dz must be 3z squared. Then del z del x is just z sub x. I mean, it's a shorthand. You can write del z del x also. But, I mean, z sub x is easier to write. Any questions with this part? Because this part is exactly differentiate z cubed with respect to z. Because g is z cubed. Then times, this one is just z sub x. So therefore you get 3z squared times z sub x. So which is this term here. So then the last term, 6xyz, this one, you see, this is function of x. This is also function of x, because z is a function of xy. So that means function of x times function of x. So obviously you got to use what? Product rule. Okay, you got to use the product rule. So what's the product rule giving you? So you can factorize out the 6y first because it's a constant. Then when you differentiate xz, right, you can differentiate x first, 1, then you whole z, plus, then when you differentiate z, you whole x, and then when you differentiate z, right, you get z sub x, because you differentiate z with respect to x, right? So therefore just z sub x, using product rule. Okay, so the whole thing is product rule, and therefore you let this be equivalent to, differentiate 1, get 0. So because you want z sub x, so you just isolate the z sub x. Okay, then there's you can see that z sub x, right? So you have 3z squared. Then this one, right, is 6y times x times z sub x, ma. So that means you plus 6xy lah. Then you throw the remaining terms on the right hand side. So you get a minus 3x squared, and then there's a 6yz here. So you minus 6yz. So then the z sub x is just this, minus 3x squared minus 6yz, divided by this, which is 3z squared plus 6xy. Then of course you can see that the common factor is 3. So you get minus x squared minus 2yz divided by z squared plus 2xy. So this is the answer for z sub x. Okay, the implicit differentiation is just here. Then because you want z sub x, that's the partial derivative. You want z sub x and z sub y later on you can do z sub y. So you can see that the z sub x is just factorized out. Then you got this 3z squared, that's this term, this green term. And then there's another blue term, 6yx or 6xy times z sub x. So factorize out. Then this one you bring across become minus 3x squared. And this one you bring across become minus 6yz. Then you just divide throughout by this factor because you want z sub x, right? So just divide. Then after you can see you can factorize out a 3. The 3 at the numerator will cancel off the 3 at the denominator. So therefore eventually you're going to get this. Any questions? Yes. This one? This part? This one? Okay, you see, you must keep in mind that because the function, the implicit function is z as a function of xy. So that means this z cube is z to the z as a function of xy cube. Okay? So that means you can treat this z cube, right, as a function g. That means g of z is z cube. Correct or not? So now, because when you're differentiating the whole equation with respect to x, you will eventually have to differentiate z cube or g with respect to x, which is here. Okay, differentiating z cube with respect to x. But your z cube, right, is actually like g, because you let g equals to z cube. Okay, this one is just for explanation purpose. In reality, right, you look at this thing, right, just differentiate with respect to the function variable first. Then after that, you just throw a z sub x or z sub y or whatever at the side, dependent on what you're differentiating with respect to. So coming back here, okay, this one is just to show you the chain rule. So when you differentiate g with respect to x, but g is a function of z, then it means you have to do del g del z first, then times del z del x. This one is like in the single derivative. The single derivative, let's say for example, let's say you are doing d dx of, let's say, f of g of x. You still remember what you did for this? This one is like df dg times dg dx. So it's exactly the same thing being applied here. So it's like dg dx, dg dz, then times dz dx. So then the del g del z is just differentiating z cubed with respect to z. So therefore it's 3z squared. Sorry? Oh, it should be z prime, right? Correct. It should be z prime. You're absolutely right. This thing, if you write as z prime, actually not wrong. But you have a problem. When you prime means you differentiate. But now got two variables, x and y. So when you prime with respect to which variable? So it's ambiguous. This you cannot write z prime already. So therefore we have to write the sub x. Sub x means you differentiate with respect to x. So therefore we no longer have a prime notation whenever you are dealing with multivariable functions. Okay? Because this one is like ambiguous. You don't know prime respect to what. Any other questions? Good. Yeah, so if you are happy with this, then z sub y actually the same thing. It's now just that you differentiate the function, right, with respect to y instead. So differentiate this expression with respect to y. Okay? So we'll look at the expression. Now differentiate x cubed with respect to y. 0, because x is a constant. Then differentiate y cubed with respect to y. 3y squared, obviously. Then differentiate z cubed with respect to y. Same thing. You have to differentiate z cubed with respect to z first. Then after that, your chain rule. Del z, del y. Z sub y. So once again, don't write z prime. Because z prime, I don't know prime with respect to what. So then the last term. So you can see the constant is what? 6x. 6x factorize out. Differentiate yz respect to y. So we're going to use product rule. Because z is also a function of y. What? So therefore, you whole z differentiate y. So you get z plus whole y differentiate z. So you get yz sub y. Then the rest, isolate terms and consolidate. Okay? So this will be easier to understand after you have understood z sub x. Any questions? It is. Z sub y. So the conventional notation, let's say you have del f del z, it is f sub z. So the sub means differentiate with respect to this variable. So therefore z sub y is del z del y. Oh, perfectly fine. You want to write it this way, it's perfectly fine also. Just you have more stuff to write. But if it's clearer for you, you can go ahead and write it in terms of the fractional notation. Any other questions? Okay, good. So now we look at higher order partial derivatives. So once again, if you can do f prime prime, f prime prime prime, right, that means you differentiate more times with respect to the variable. You can also do it the same way for a multivariable function. So you can see that we can get our f sub x, but we can also get our f sub xx. That means you differentiate one more time, that's all. Can also get f sub xxx, right? Just differentiate one more time, and so forth. Okay, so those are higher order partial derivatives. So you can see that function here, now if you differentiate once, right, with respect to x, then obviously you get the 3x squared because the y squared is a constant. So you get 3x squared y squared for the first term. Then for the second term, differentiate cosine is going to give you minus sign. Okay, then the angle no change. But you need to use chain rule. So differentiate xy with respect to x. That means you have the constant y being chain rule out. So f sub x, you can always differentiate again, right? So that you get your f sub xx. So differentiating again, you can see that the 2 bring down. So become 6x. Y squared keep as constant. Then minus. So differentiate sine, get cosine. Then after that, differentiate xy with respect to x. You go in, chain rule out another y. So giving you y squared. You can see, Okay, so this one nothing much. This one just differentiate one more time, that's all. So the same thing goes with f sub yy. Is that alright? So this one just differentiate one more time if they ask for a next higher partial derivative. Any questions? So then what is the meaning of f sub xx and f sub yy? Okay, before I go to that, okay, then the thing here is, right, there can also be mixed partial derivatives because, you see, after I differentiate respect to x, I get my f sub x. But I can differentiate f sub x with respect to y. Okay, because f sub x is still generally a function of x and y. As you can see from here, it contains x and y. So which implies that, right, if I want, I can also differentiate this function respect to y. I need not keep on differentiating respect to x. So which is what happened here. So this is called a mixed partial, or mixed partial derivative. So which means this expression, so you follow the order. You do respect to x first, then after that you do respect to y. Okay, so you can see from here, right? So it's actually del y on f sub x. So this one nothing much. This one you just differentiate this expression respect to y. You can see you bring down the 2, then it becomes 6. Then the y become power minus 1. 2 minus 1 become 1. Then this one, you have to use product rule. Because it is y times sine xy ma. So it's function of y times function of y. So therefore use product rule, you're going to get this expression. Okay, and this is exactly your f sub xy. Okay, so in this case, we denote this f sub xy as del square f del y del x. Because you are doing del f del x first. Then after that you do del y. So therefore you have y first followed by x. Following the correct order in that sense. Okay, then this f of xy you differentiate respect to y. You have f sub y equals to this expression. Then you can also do differentiating respect to x now. Right, so this is the other mixed partial. Okay, f sub yx. Then if you differentiate this, right, you're going to get this. Then you might observe that actually the two expressions are the same. So we have f sub xy equal to f sub yx. Okay, and this is always true one. This thing is always true as long as your mixed partials are continuous. You can see that the functions are continuous. So as long as it's made from continuous functions, right, this is always true. Okay, and we can prove this actually. So we'll be proving this in tutorial 7, not tutorial 6, the next one, tutorial 7. Because tutorial 7 deals with integration. So we're going to use integration to prove this identity. Okay? So, but this is just a result. If you want to get the mixed partials, right, you can either do x first, then y, or you can do y first, then x, and the result will be the same. Any questions with the higher order partial derivatives or mixed partials? No, this one quite easy. I just differentiate respect to whatever variable that they ask you to. Okay, but then this one got graphical meaning one, right? So this is more of like a sneak preview into the second derivative, but we'll deal more on the second derivative in Math 3, okay? Because this thing is actually important in optimization. Optimization is in Math 3, okay? But let me just introduce here. So you can see that what is actually f sub xx saying? Now, f sub xx is the rate of change of f sub x, correct or not? Because f sub x is looking at the rate of change of f, right? So f sub xx is looking at the rate of change of f sub x. So therefore, we just need to look at the f sub x. So let's say this curve, f sub x at earlier x, at a smaller x, is negative. Then f sub x at this minimum point is 0, right? Because the gradient or the slope is 0. Then f sub x at a later x is positive, and it's getting more and more positive. You can see steeper and steeper. So what happens here is that, right, you can say that the f sub x is increasing, correct or not? Because go from negative to 0 and then to positive and getting more and more positive. So the f sub x is always increasing. But when f sub x is always increasing, that means the rate of change is positive, what? Right? So therefore, f sub xx is more than 0, which is correct because it's giving us a constant 2. 2 is always more than 0. Is that right? Then, of course, the same analysis can be done for f sub yy. Okay? It's just that you are looking at this being the y direction. Okay? So this can be x, this can be y. Right? You are going to see this kind of smiley face curve. So therefore, it is also going to give you a positive rate of change for your slope of the gradient. Any questions with this understanding? Like the gradient increasing, so the derivative of the gradient, which is f sub xx and f sub yy, must be positive. Yes? Yes. Oh, no. As you go from the left to the right, the f sub x is slope of tangent. This is like f prime. So therefore, you can see the slope. This slope, downward sloping, so the slope is negative. Then this one slope 0. Then this one slope positive. Then if you go to this point, right, at the even later x, right, the slope is even more positive, meaning to say bigger lah, positively bigger. So what does that imply? That implies that, right, the slope f sub x is increasing ma. This is increasing. So when some function is increasing, the rate of change of the function must be positive. Agree? Because that's what increasing means, right? That's what rate of change means. If rate of change is positive, right, that means the function is increasing. This 2 is just, because I differentiate 2x plus y respect to x. So then it's just 2 lor. It's only for this function. For a different function, then the f sub xx is going to be a different number or different function. Because generally, right, the f sub xx or any derivative is a function of x and y. Is that right? Any other questions? Yes. This curve can only see f sub xx. Okay, because you can see that, let's say for example, this one is this red color intersection curve. So that means I already fixed y already. So after I fix y, that means this is x or. So that means I can only see f sub xx, right, from this graph. I cannot see f sub yy. In order for me to see f sub yy, I must go back to this one, the orange color plane. You see orange color plane? That means my f sub yy is also positive, because it goes from negative to 0 to positive. So f sub yy is 2, also positive. It's a constant 2 lah, meaning to say it is always the tangent, right? The slope of the tangent is always changing at a rate of 2, of positive 2. Okay? Coming back here. Yeah, so when your f sub xx is positive, now you notice something. You are definitely going to get this kind of smiley face curve. Right? So this is a convex curve that looks like a smiley face. Okay? So we call this convex. Convex means your f sub xx is positive. So this convex means f sub xx or f sub yy, whatever, is positive. Then we call it convex. So because positive, it will always result in a smiley face or part of a smiley face. Okay? So therefore this is called convex. Then if you have f sub xx less than 0, f sub xx, if you have less than 0, so you can see this guy is less than 0. Because slope here is positive. Then go to 0, then go to negative. So therefore this is decreasing. That means the slope, right, is decreasing. So if the slope is decreasing, that means the f sub xx must be negative. Then we call that a concave curve. So got two types. Smiley face is convex. Then sad face is concave. Okay, so maybe I also write here that the f sub x is decreasing. So this is just introduction, because concavity or convexity of a function, right, we will deal with that in Math 3. So actually, concavity important, right, in the sense that if you have a function that is fully convex, then the minimum you get is called the global minimum. That means it's true minimum. In the whole functional space, right, you only have this one minimum that is the true global minimum. Okay, this one important. Because when we do optimization, let's say we're finding a minimum of a function, we want the best minimum. We don't want like some like not so good minimum. Okay, so therefore to prove that the function is convex, right, will depend on checking its f sub xx or f sub yy, etc. Okay, so this one not to worry too much. This one, Math 3 will be diving into the details because we'll be doing optimization. Okay, then optimization is actually the prelude to machine learning. Machine learning is actually optimization. Okay, so having understood the second derivatives, we can also understand mixed partial derivatives. Okay, but this one a bit more funky. So let me illustrate to you what is actually your f sub xy. Okay, now you see. Now, let's say I have this function curve. Okay, so this function surface, right? Same function, x squared plus xy plus y squared. I can plot it in Desmos or GeoGebra easily. Then now, you look at the plane y equals to 1 and y equals to 2. So at the plane y equals to 1, right? You can see the y here. Okay, so at y equals to 1, I never draw the plane just to be clear. Okay? So if you have the intersection between a plane at y equals to 1 and the surface, you are going to get this red color curve. Okay? I mean, I can roughly draw to show you the intersection. You see? This is the plane. Okay? Not very nice, but the red color plane, right, intersect the blue surface. You are going to get this red color curve. Okay? Can understand that? So therefore, I can also get another intersection curve with the plane y equals to 2. So which is this purple color plane. Can Okay, so now, think about it. When I look at the intersection curves, the red and the purple curves squarely, that means I look at the side. Okay, I see this, right? I see this. So let's say I have at x equal to 0. At x equals to 0. Now x equals to 0 is here. Now I can draw two slopes, right? One slope for the red curve, the other slope for the blue curve or purple color curve. Okay? So what did I realize? I realized that at x equals to 0, the slope originally is 1. Now increase to 2. Okay, I repeat that again. The slope for the red curve is 1. Then the slope for the purple color curve is 2. You see, it got steeper, correct? But this is f sub x, right? The two values are f sub x. Why is it f sub x? Because you are looking at the slope in the zx plane. Okay, that means if you step in the x direction at x equals to 0, you're going to experience a slope of 1 and 2 respectively for the two curves. Understand, right? But you look at the two curves. One is at y equals to 1, the red one. The other one is at y equals to 2. So that means if you want to describe the change from this f sub x to the other f sub x here, that means you are taking a step in the y direction, right? So therefore, this is what? F sub xy. F sub x, then take in the y direction, going from red to purple. So therefore, you can see f sub xy is 1. Why is it 1? Because increase from 1 to 2, what? Okay? So you can see from here, right? How do I get this 1 and 2? Very simple. I just sub in value only. So the f sub x at x equals to 0, y equals to whatever. Okay? So for the red one, right? Because the y is 1. So therefore I get 1 because it's 2 times 0 plus 1 is this function. Okay? So then the same thing for this y equals to 2. So 2 times x equals to 0 plus y. So it's plus 2. So therefore I have 2. Okay? So you can see that if you step in the y direction, you are going to have the red curve to the purple curve. So then the f sub x actually increased from 1 to 2. So what is the increase here? 1. So that's the meaning of f sub xy. Is that right? So you can also analyze f sub yx. Okay, but your plane will not be like that. The curve will not be in this orientation. It will be in the other orientation. Okay, but doesn't matter. I think you can understand. If you can understand this, right, you can understand f sub yx also. Is that right? So this one need a bit of visualization, a 3D spatial visualization. Is that okay? Any questions? Okay, if you cannot visualize, actually it's fine. Right? The main thing is you can do the operation, right? You can do the differentiation respect to whatever variable. That will be more important. Okay? This visualization actually also important if you really want to understand what are mixed partials. Okay? Okay, this is a big mess. So I'm going to repeat the whole thing. Repeat writing the whole thing. Hold on. So this is an exercise to test you on the understanding of the second derivatives as well as the mixed partials. Okay? From a different kind of viewpoint. Okay. So what are these numbers? These numbers are the function values at the coordinate that is given. Okay, because I don't know what's the function, right? The function is not given. So therefore, if you look at this 2, right, what is the meaning of the 2 here? This is f of x equals to 2, y equals to 3. So x of 2, 3 equals to the value of 2. So this is the 2, the function value. Understand? So then what about this number? This number is f of 3, 1. Because the x is 3, y is 1. And the answer is 4. The function value is 4. So therefore you get a 4 here. Okay? So of course you can calculate the other I mean, you can label the other points, but not necessary. Okay? So this will be for your values of f of xy. So now we want to estimate f sub xx, yy, xy, and yx at 1, 1. At this position 1, 1. How? Okay? So certainly, in order to get f sub xx, right, you must get f sub x first, what? Correct or not? Without f sub x, you cannot get f sub xx. So therefore, let's see. So how to get f sub xx? How to get f sub x? So same thing, I draw the thing. So at x equals to 1, y equals to 1. What is the f sub x? So what is f sub x? F sub x is that you take a step in the x direction, ma. So therefore, at 1, 1, you must take a step in the x direction and see what's the function value. Okay? So you notice that when you step from this point to the other point in the x direction, the function value increased from 3 to 4, right? Correct or not? So what is f sub x? So f sub x at 1, 1 must be approximately, okay, by right is take the limit, correct or not? F at, so you can see that this is 1 plus h, because x is 1, ma. 1 plus a step h, okay? Then after that, at y value of 1 minus f at 1, 1 divided by h. So you have to take the limit, right? H go to 0. By right, you have to take this limit. But you can take the limit only when you know the function f. But now the function f not given what? So that's why they ask you to estimate. So we say that, oh, don't take the limit, just approximate. Okay? Approximate by the gradient of the secant instead of finding the gradient of the tangent. Okay? Which is actually reasonable if your h is small. Can you see? This one? Can So therefore, we take a step. H equals to 1. Isn't this h equals to 1? When you take a step, h equals to 1, right? So therefore, I can write it this way. So therefore, this expression, if I take a step of h equals to 1, so I get 4 minus 3, correct or not? Because this will be what? F of 1 plus 1, comma 1, minus f of 1, 1, divide by 1, ma. But then this is just f of 2, 1, what? So f of 2, 1 is 4, So isn't this 4 minus 3 divided by 1? So therefore this is 1, So f sub x at 1, 1 is 1. So it's approximated to be 1. Any objections? No, not yet. That one is f sub xx. Now it's f sub x first. So if you understand this, right, then you can also fill in the f sub x for 2, 1. So 2, 1 means 4 go to 4. 4 go to 4. So you tell me, 4 go to 4, what's the change? What's the f sub x at 2, 1? 4 go to 4. Just now is 3 go to 4, so increase by 1, makes sense. This one 4 go to 4. So the increase must be what? 0, also this one must be 0. So at 2, 1, right, the function got no increase. It's not increasing. 4 go to 4, ma. Then what about at y equals to 2? Can calculate also. So at y equals to 2, you get 1 here. 1 go to 1, 0. Then this one, 1 go to 2, 1. Okay? Then of course you can do the 3 one also, right? But actually this is good enough. You don't need to do the 3. I mean, if you want, you can do. Okay? But this is good enough. The reason is because now we want to find f sub xx at 1, 1. So f sub xx at 1, 1. That means you have to go from here to here, ma. Correct or not? You just repeat the same analysis for this instead of this. Okay, if you do the analysis for this, you are going to get f sub x. If you do the analysis again on this, you're going to get f sub xx. Isn't that logical? So then you can see this one is what? 0 minus 1 divided by the step of 1. So the answer is minus 1. Because 1 to 0. 1 to 0 is decreasing. So it must be minus 1. Is that right? Okay, then you tell me. See if you can guess. What is f sub xy at 1, 1? Let's see if you can extrapolate the understanding. What do you think is f sub xy at the position 1, 1. Ah, very good. F sub xy, because y ma, so you must step in the y direction. Okay, you look at the f sub x graph, but because you are doing differentiation respect to y, what? So therefore you must step in the y direction. So therefore it is also 0 minus 1 over 1. So it's also minus 1. I mean, just happen to be lah. Okay, the same for f sub xx and f sub xy. It's just coincidence. Is that okay? So what about the f sub yy? F sub yy. Can do also. You have to get a graph that is for f sub y. Okay, which is not difficult if you understand the logic now. So therefore 1, 1, 2, 2. Yeah, that's good enough. Okay, so at this point, what is the f sub y? It means now you have to move up already. So this point must be what? Minus 2. Because it is 3 drop to 1. 3 drop to 1. Or 1 minus 3 divided by 1. Because you are taking step in the positive y direction. So this must be a minus 2. Okay, then at 1, 2, 1 drop to 0. Minus 1. Then at 2, 1, 4 drop to 1. Minus 3. At 2, 2, 1 increase to 2. So 1. So therefore you can do your f sub yy already at 1, 1. You can see 1, 1, right? So you have to step in the y direction. So it's minus 2 to minus 1. Increase by 1. Minus 1 minus minus 2. Divide by 1. So therefore this guy is what? 1. So then if you get the f sub yx, f sub yx at 1, 1. You can see minus 2 drop to minus 3. So therefore this is minus 3 minus minus 2 divided by 1. So minus 1. Okay? Then we will notice something correct. This and this, they are equal. So I hope this exercise demonstrated the meaning of the partial derivatives as well as the second and mixed partial derivatives. Okay? This one is just like looking at points. Looking at points instead of looking at the graph. Graph there's a meaning, right? You have to like get the intersection and then look at the slope and whatnot. Right? But you can also look at function values, right? And you can roughly estimate what are the derivative values. Okay? Main thing is to let you understand what are the derivatives and mixed partials and second derivatives as well. Got meaning one. Okay? Only when you understand the meaning, then you can apply to the solving of real world problems. Can? Okay, so with that, I think we take a short break, digesting break again. Right? If there's anything unclear, you can come and ask me. So let's have a break till 3:20. So 1, 2 is, you want f sub y or f sub x? F sub y. So it's at 1, or 1, 2 is here, correct? So if it's 1, 2, right? Wait, can I show that? Yeah, you can. Wait. Oh, cannot 1, 2 I cannot show, but 2, 1 I can show. Because 1, 2 I cannot show. Because I don't have the f sub x at 3, at this 1, 3. If I need to show 1, 2, right? 1, 2, that means this point. I need to know what is the f sub y here. I need one more. I want one more value here to get the f sub y here. So, but then if it's at 2, 1, I can show. So let's say if you want 2, 1, right, which is this. So the f sub y at 2, 1, you can see that minus 3 go to 1. So it's 4. Because it's 1 minus minus 3 divided by 1. Because minus 3 go to 1 is increased by 4. Huh? Oh, how I determine h? Because I don't know any of the function values in between any two integers. So I cannot take a h of 1. Take a h of 1. Unless I know what is the value like at 1.5. Then I can take a half a step, like for example a step of a step of 0.5. But I don't know I don't know what is the value here. So therefore I only know the values, function values, right, at the integer points. So therefore my step, smaller step will be 1. Yeah, the smallest possible. That will give you the best approximation. Because you must understand that the better approximation comes as your h is smaller. If you jump 2, possible. But then the estimation will not be as good as if you take the smaller step. Is that right? Can okay. Okay, we are going to go on to something that is very confusing. Okay, but actually not so confusing, I'm just scaring you. So first of all, now we got to look at this concept called linear approximation. Okay, actually the concept quite straightforward. So what is linear approximation? Okay, I tell later then I tell you why is it that they want to do this lah. Okay, because initially when you look at this, right, there's no good reason to do this. Okay, but there's actually a good reason. So the thing is like that. Okay, let's say you have a function f of x, a blue curve. Okay, and then now, right, instead of calculating the function value, right, let's say f of x at this point, you are now going to use a tangent to approximate the function value here. Okay, so now you just want an approximation of the function value at x using a known function value at a, at this x equals to a. Okay, so now the story is, right, you know the function value at a, but you don't know the function value at x. Okay, so therefore you want to make an approximation using the tangent. Okay, so one can see that, right, what is the error? The error is actually here. This is the approximation error. Okay, because the actual value is here. Wait, my arrow not very accurate. Okay, so you can see that this is the actual function value because it's coming from the blue curve. This is the actual function value. But if you use the tangent, right, it is this value. So there's an error here. Okay, so obviously you can say that, right, as the point x go closer and closer to the point A, then the error is going to decrease lah. Like for example, if I come to here, right, then my error is just like this small error. Then if I come to here, right, then it's almost cannot see from the graph. Okay, so therefore as x approaches A, your error becomes smaller and smaller. Okay, so therefore what is the linear approximation? What is this linear approximation value which I call L of x? Okay, L that represents linear. So I can just simply use the slope of the tangent, very simple. Okay, because I know the slope of the tangent is what? The slope of the tangent at point A is just f prime A. Correct or not? I sub in A I differentiate the function f first, right? Then I sub in A. So therefore I know that the slope here is f prime A, but the slope is also given by change in f over change in x. So what is the change in f? Now if I use the tangent approximation, the change in f must be L of x minus f of A, this one, divided by x minus A. So that is exactly equivalent to f prime A. Okay, so therefore, using this slope expression, right, I can isolate L of x. So you can see that if I know what is the function value at A, and I just use the gradient, I take the gradient multiplied by x minus A, is going to give me this increase. This is the change in f. Okay? Can you see? So, okay, maybe I shouldn't use the stupid light blue color. Let me change that into orange color. Clearer. Okay? So this is what? This is like your change in f, which is this guy. Right? So f of A plus the change in f, right, is going to be the linear approximated value. Okay? So where does this come from? You can see this x minus A just multiply across. Then the minus f of A I bring to the left hand side. So become plus f of A. Any questions on the linear approximation for a single variable function using some tangent line? Okay, so I'm going to tell you why is it that you want to do the linear approximation. Because, I mean, initially, right, this looks very stupid. Why I say stupid? Because why not you just calculate the f of x value at any x? Why you need to go and make your life difficult, right? Go and do linear approximation. Because linear approximation is an approximation, right? So it's not as accurate. So why not just fit in the x, fit into the function f, and then just calculate the number directly. You know, why you want to go and do the approximation? Okay, the answer is, we don't know what is the function f of x. Okay, the answer is, this linear approximation works the best, right, when we don't know the function f of x. Now you look at this expression. It didn't require us to know the function f of x, you know. We just need to know some value of the function. We don't know what's f of x, but we know some value of the function at some point a. Okay, that means we know a, b lah. Like b is the f of a, right? And we only need to know the derivative of the function. Okay, we only need to know the derivative, right? And then we can multiply by a step size to approximate what's the function value at some other x. Okay, so this happens when, right, we do not know what is the function f of x. This becomes very useful. Okay, and then maybe you have the next logical question is, hey, how come you don't know the function f of x, ma? How come you don't know the function f of x? I thought it's always defined. Now the answer is, right, in Math 2, you will learn this thing called mathematical modeling. And then the mathematical model of some engineering or physical systems is going to result in an equation that you have to solve for f of x. That means you don't know what's f of x. You're supposed to solve for f of x. Then when you're solving for f of x, right, one of the solutions is that the linear approximation forms part of the solution. Okay? So that one in Math 2, you will like appreciate this better, but I tell you the story first. Okay? So, I mean, not very critical lah. This is just the story. Okay, what's critical is this. Okay, is this. Okay, this one a bit more complicated. Okay, so this is our linear approximation, right, for the single variable function. Now, what about for a function of two variables? Okay, so now, single variable, you use tangent line. Just now we already discussed, this one is tangent line, what? So therefore, you are using tangent line. Okay, you use tangent line. So for multi-variable functions, like function of two variable, right, you cannot just use the tangent line, right? Because if you look at f of xy, it is representing this surface, what? Correct or not? So what is the corresponding tangent line to the function of xy? It is the tangent plane. The tangent line becomes the tangent plane when you go from 2D to 3D. That means you increase the tangent line with one more dimension. So it becomes tangent plane, Correct or not? So you see, this f of a term, right, must be replaced by f of ab. There, the function value at some ab, x equals to a, f equals to b. X equals to a, y equals to b. Okay, so you must know what is the function value at ab, at some ab. Okay, it's just like where you evaluate this f of a in the single variable function. Now, you can also take a step in the x direction. So you see, take a step in the x direction, right, in a single variable function. Now, same thing, take a step in the x direction. So by now, you should know that the f prime is like f sub x in the x direction, okay? So you can say x minus a, it's the same thing. Now, if you take a step in the x direction, right, so this is what? This is the change in f in the x direction, okay? So this guy, this is the delta f, right, in the x direction, in x direction. Okay, so it's actually represented by this thing, change in f in the x direction. Okay, but xy is here, xy is not here. So that means you got to step in the y direction to get to y, to get from b to y. So therefore, this green color part, right, is this. So you can see the similarity between the two terms. Okay, so this one is the gradient in x times delta x. This is the gradient in y times delta y. So therefore, this expression, the green part, is the change in f but in the y direction. Okay, so it's this guy. Can? So this is the delta f in y direction. Any objections? Okay, so now, what is the tangent approximated value, L of xy? Now you walk in the x, then you come to this point. It's like you walk in the x, you come to this point. So let's say originally you're here. Okay, you walk x minus a in the x direction, then you come to this point. Then you increase in f already. Then after that you continue to walk in this direction, in the y direction, then you come to this point. Okay? So therefore you sum up the delta f in x to the delta f in y to the original height that you are at, right? Then you come to L of xy already. So understand this, okay? So this is the tangent plane approximation, the linear approximation for a function of two variables. Any questions? Can So if I have a z variable, okay lah, then plus one more lah, plus f sub z lah, times a step in the z direction. So that's the linear approximation for a function of three variables. Okay? So you just keep on adding, that's all, if you have more variables. So that's the crux of the linear approximation. And why is it that we need to understand this? Okay, because, okay, first of all, any questions with this or not? Okay? So now, you can imagine, right, if, obviously, what's the error? The error is this thing, this error. This error is very big. This is the error. Okay, that's why this is approximately, right? But this is a big error, as you can see. How to reduce the error? Now, to reduce the error, I just choose an xy that is very close to AB, right? Or I can choose an AB that is very close to xy, the same idea lah. Okay, so which means you can imagine that if I just draw you this part of the diagram, now then you almost cannot differentiate the curvature of the surface to the tangent plane. Agree, right? Agree, Okay, so if you agree with that, then you see that if I change this AB to xy, so I just change the AB to xy, then I change this point, which is away from xy, right, as x plus dx, y plus dy. Okay, so I think you can see where this is going because you can see the d term here, right? So which means if my dx and dy approach 0, so dx, dy approach 0 will mean that, right, I go very close to this point, to this corner point here. Then I can see that the function is going to approach the tangent plane. So I cannot tell what's the difference between the function and the tangent plane already. Okay, because it's like coincidental lah. So you can see like the red tangent plane, the purple tangent plane, right, is coincidental with the red function. Okay, so, which means I can write this, right? This is f of x plus dx, y plus dy is equal to f of AB now become f of xy. Because AB become xy ma. Then this is f sub x times change in x, right? But what's the change in x? dx. Then this is the f sub y times change in y. Then this is dy, because the change in y now becomes dy. So, as dx and dy approach 0, this becomes equal because the tangent plane is exactly the function surface. So therefore, it becomes equality sign already, no longer approximation. Okay? So this is just coming from the linear approximation, right? When you have the dx, dy very close to your xy point, to your original point. Okay? So what's important here, right, is that you just bring this f of xy across. Just bring across, Then you can see this part. So this is f of x plus dx, y plus dy, which is this point, minus f of xy. So therefore, it is giving you a total change in f. So the total change in f, I call that df. Okay? And it is the sum of what? It is the sum of this part, which is the blue part, the partial change in f in the x direction, plus the partial change in y in the y direction. So it's the blue arrow plus the green arrow. You see? So the total change must be equivalent to the sum of partial changes. Okay? So therefore this is like what? Change in f due to infinitesimal change in x, because dx is an infinitesimal change. And the same goes with the second term in green. Okay, so total change is just a simple sum of partial changes. And in this case, the df, right, we call that the total differential. Okay? Right? So I can see that this is tough. Okay, but I'm going to tell you why is it that we go through this thing. Because in order to define the chain rule, okay, very important chain rule, right? So in order to define the chain rule for partial derivatives, right, we need this total differential. Okay, why? You see, Next one is the chain rule already. Now, how to differentiate f with respect to t, for example. Now, f is a function of xy. Okay? So therefore, if I can write a composite function, f of x of t, y of t. So which means that I can differentiate f with respect to t, differentiate f with respect to t. Now, how to differentiate f with respect to t if I have a composite function? I need to use the chain rule. So therefore, df dt is exactly that, trying to differentiate f with respect to t. If I divide by dt here, I must divide by dt here. And I must divide by dt here. Okay? So this is the chain rule when you have a function of two variables xy. Can you see that? Okay? And it is coming, or it is being derived from the total differential. So this will bring me to the next slide here. Okay? So if you recall, for single variable composite functions, right? For example, g of t equals to f of x of t. This is just how we demonstrated this idea also, right? The chain rule is just df dx times dx dt. Okay? Can you see this one? Right, this one is the chain rule for single variable function. Then if you have multi-variable composite function, then the chain rule applies in a similar manner, because we just need to divide the total differential by dt. So therefore we have this expression. Can you see? F dt is just del f del x times dx dt. Because x is a function of t, so therefore you can do a differential, a differentiation with respect to t on x as well as on y. Okay? So therefore this is the chain rule for partial, for multivariable functions. Okay? And what is the meaning here, right? Isn't it important? This one? Okay, so what is this del f del t? Or what is this df dt? Now, this means, right, as t change, how does f change? As t change, how does f change, right? Now, you must understand that, look at the function here. When t change, it's going to cause x to change, because x is a function of t. So therefore, when x change, it's going to cause f to change, because f is a function of x. So therefore, how is this change being accounted for? Accounted for by this term. Can you see? T change cause x to change. X change cause f to change. So the rate of change in f due to the rate of change in x. That's the first term. This term. Okay? So then, of course, your f is also a function of y. And y is a function of t. So therefore, t change cause y to change. Y change cause f to change. Second term. Is that right? Can? So therefore, this is the chain rule applied to multivariable functions. Any questions? Okay, no questions because you don't know what's going on. So therefore, now I'm going to make an example. Right? Let's look at an example and then you will see what is going on with this. Okay? So actually, I mean, it's more difficult than it looks. Seriously. Okay, we're going to come back to this again. Okay, now I'm going to go through this example. Okay, let me go through this example. Okay, just directly from here. Okay, it's quite okay. So you can see, now g of t is a composite function, but I introduced z also. So f of x, y, z. Can I f of x, y, z? So you can see the function is given by x, y over z. Okay, simple function. But this, because the x itself, this x itself, right, is a function of t. Same goes with y and z. And the functions are given here. Okay? So now, when I evaluate my g prime t, right, I'm differentiating f with respect to t. Correct? Differentiate here, must differentiate here also, what? Correct? Okay, so now, what is the chain rule? F sub x times x sub t. So this first term, right, this first term is del f del x times dx dt. This very first term. Okay, just a right shorthand. Can? Then if you understand this, right, then you got to understand this also. Del f del y times del y del t. So del f del y times del y del t. That's the second term. Okay? Then the third term is del f del z times del z del t. Okay? Or in this case, it should be d because it's only a function of a single variable t for x, y, and z. So more technically correct is d. D or del actually doesn't matter, just some small change. Okay, you see, this is this ma. Then actually once you write down the chain rule, then you just find the individual expressions. So you see, f sub x is what? Y over z ma, because x is a variable, y and z are constants. So therefore you get y over z. Then x sub t is what? X sub t is 2t. Because you just differentiate x by differentiate x with respect to t. So you get 2t. Then f sub y is what? X over z. Then y sub t is what? 1 over t. F sub z is what? X, y, the z to the power of minus 1, bring down the minus 1. Then z minus 1 becomes z to the power of minus 2. So therefore, minus xy over z square. Then differentiate z with respect to t, minus 1 over t square. Is that okay? So this one actually chain rule, nothing much. Then eventually just find the individual derivatives, then simplify. Okay, so of course I didn't simplify here. Let me simplify together with you, and you will see that you get the answer. Okay, you put one side first. Okay, how to simplify? Because you must understand, this is a function of t what? But then this got x, y, z inside, so not finalized. But you can finalize it easily, because all your x, y, z in terms of t are given ma. So therefore, what is this? This is ln t, because y is ln t, divided by 1 over t, then times the 2t. That's your first term. So you convert everything to t. Then x is t squared divided by 1 over t times 1 over t. That's the second term. Then the third term is minus xy. So minus t squared times ln t divided by 1 over t square. Then times minus 1 over t square. Is that okay? So if you simplify this, you are going to get this. If you simplify this, right, just cancel, whatever terms, you're going to get this. Sum up, you're going to get this. So therefore, this is the chain rule being applied to find g prime t. Any questions on the chain rule? Actually, you notice that actually it's not as difficult as it looks like. When you differentiate here with respect to t, make sure you always end with the sub t. So certainly, can I differentiate directly on g of t to get g prime t? Can. Because you can always sub in the functions here, sub into xy over z, which is what happened in the last line. Okay, so if you sub in, you get this expression, you're going to get t cubed ln t. So this is actually your g of t. Okay? Then you can differentiate directly. Now if you differentiate directly, you use the product rule, and you're going to get this expression, which is actually the same as this. And that's to be expected. Because both are g prime t. It must be the same. So this is like checking your chain rule, or rather, in this example, verifying the chain rule. In reality, this is too complicated to evaluate, like too big already. Okay? So therefore, we perform the chain rule, it is easier. That's why we come up with the chain rule. Any questions? Okay, before we complete today's lesson, one last part. You can also have the interior functions being multivariable functions as well. Just now is x of t, y of t, right? Now is x of st, y of st. Can also what? Okay, that means the interior functions themselves can also be multivariable functions. So if that's the case, your f of xy, right, will return you a function of st. So let's call that g of st. So if you want, you can get the g sub s. That means your del g del s. So partial derivative now. You see, but actually nothing much, right? If you are differentiating with respect to s, make sure you have ending with sub s. Okay? If you are differentiating with respect to t, you must make sure you have ending with sub t. Makes sense, right? Okay? So you can see, look at this expression. Actually nothing new. Right? This expression looks like the previous expression. Okay? And if I do with respect to s, then you just change all the sub t to sub s. Is that right? Can Okay? So the idea here is, right, you can see, this one, if you cancel the del x, and you cancel the del y, right, you have del f, del s plus del f, del s. Okay? So that is going to give you your total del f, del s. This first term is del f, del s due to change in x. This one is del f, del s due to change in y. Okay? So it must be like that, right? So that you don't write the wrong expression. So therefore, this will be the last example for today. Okay. See, I give you the f of xy, multivariable function. Then x itself is a function of st. Y itself is a function of st. Okay, right? So now if I want to find g sub s, right, I just differentiate respect to s on this function f. But I need to use the chain rule. So it becomes del f del x, because there's an x there, times del x del s what? Plus del f del y, there's a y there, times del y del s. So chain rule. So therefore del f del x is what? Differentiate 2x y cubed. Then del x del s, look at this. So differentiate e to the st respect to s. So t is chain root down. Okay, so the same goes with del f del y. Bring down the 3. So 3x squared y squared, then del y del s is just t cosine s. Then after that, you need to sub in, because eventually you must have only s and t, no x and y. So just sub in. Okay, x is e to the st, y cubed will be t sine s whole thing cubed. Okay, so if I underline, maybe looking at something like that. Can? Okay, so same thing goes with the second term. So you just sub in the variables, the functions, simplify, you get the answer in st. So chain rule difficult or not? Actually not so difficult. Right? It's not that bad, right? It's just that the derivation through the tangent plane, understanding the total differential, right? That one a little bit hairy lah. Okay, but when I ask you to just apply chain rule and differentiate, actually it's not difficult. Any questions? Can Okay, so why is it that we need to go through this total differential thing, right? I tell you the reason. It's because given a multivariable function, we are not exactly confident, right, that when you differentiate, this is going to be a plus. We are not exactly confident, right, before derivation, that it is going to be just a simple sum of partial changes. Okay, because it could be multiplication, what? It could be this multiplied to this, meaning to say the change in x, right, multiplied to the change in y. Okay, why has it got to be a simple sum? Right? So the tangent plane understanding, right, actually tells us that it's just a simple sum. Okay? So much so that we can apply the simple sum to our chain rule. Okay? So that's the reason for the tangent plane understanding. Okay, then that's all for today. Okay, this part, I'll just fill in the answers, okay, in the writings and upload it. So then it's done for topic 6.